All right. Yeah. Yeah. Thanks a lot for the invitation and having me to speak here, and thanks for everyone for tuning in here. I guess I really do encourage people to ask questions. So yeah, feel free to interrupt whenever. Yeah, it's great to speak here at this tropical conference, I guess. I mean, I'm not a tropical geometer, but I certainly I view this as a sort of nice application of tropical geometry. So yeah. Okay, so let me begin. So everything here is joined with Johannes Nicaise. Well, it's basically related to rationality problems of hypersurfaces and complete intersections. And everything is in characteristic 0 because we need the resolution of singularities. Yeah, just a first definition, just to set the stage. We say that two varieties, X and Y, are stably birational if they become birational after taking a product with a projective space. This is an equivalence relation. Yeah, and we say that X is stably rational if it's stably birational to a point or projective space. So of course, rational varieties are stably irrational. And that's of course why we're interested in this relation. It's sort of interested, or it's easier to study stable birationality instead of rationality. So as a sort of one sentence summary of the paper, and also the talk, the paper with Johannes is devoted to sort of a general method for the rationality problem for complete intersections in toric varieties. Okay, so before I begin, let me just sort of survey a little bit what's known about, say, hypersurfaces in projective space. So the main theorem today will be the following theorem, and I'll relate this to the sort of history in a second. And it says that the very general quartic fivefold is stably irrational. Yeah, not stably irrational. Right. Yeah, so that's maybe the most striking application of this these techniques that I'll explain. So this is maybe yeah, this is the main application, but we also give sort of new proofs of other for other hypersurfaces in projective space. Yeah, okay, let me survey a little bit what was known before. So here you see a table of, well, we have degrees downwards and then dimensions in the horizontal direction. So everything in green is known to be rational. We have this sort of special cubic surface thing, which is of course rational. But most of the other boxes here are stably irrational. And yeah, this is sort of a quick summary of what's known. So for cubic threefolds, we have the sort of famous result of Clements and Griffiths, who show that a general cubic threefold is not rational. So this is marked in orange because it's not really known whether this is stably irrational, but it's known that it's not rational. A priori, it could be that, you know, some sort of vector bundle or something over and a cubic threefold is rational. But the other cases here are known to be stably irrational. So I guess There are various techniques here. Maybe the earliest result was due to Collar, using a technique like a mod P technique. And then there was a breakthrough using the decomposition of the diagonal technique, using from Collot-Toulet and Pirutka. Of course, basing this on work by Voisin. I mean, she's really the sort of one who started this whole development. And from there on, it was, I mean, we got many new cases by Totaro and maybe especially Stefan Schreider, who covered sort of a result in higher dimensions, which was very surprising, that he had some sort of logarithmic bounds for the degrees. So this is in higher dimensions by far the strongest result we have. So our main contribution is this sort of yellow box here, the quartic fivefold. Yeah. All right. So, but of course there are some other applications as well. So the method is not limited to hypersurfaces. So for instance, we can talk about complete intersections in P6, for instance. So if you take a very general complete intersection of a quadric and a cubic, this is stably irrational if this has dimension at most four. Okay, so this is a class of varieties that sort of behave like rational varieties. They have many of they have essentially the Hodge numbers of a rational variety, and then they're rational connected. So it's hard to prove that these are irrational. And in fact, there's a sort of interesting history of these particular complete intersections going back to the Leroth problem. So it was known that these were irrational in dimension 3. Right. So yeah, in fact, Fano from 1908, he claimed to have a proof for irrationality in the case of threefolds. That's a complete intersection of a quadric and a cubic in P5. But of course, it turned out to be that to be incorrect. And yeah, one reason why this is interesting is that it was known that these are unirational. So then there's at least a map from P3 onto this threefold, which is of degree 2, I think. So this was sort of one of the early candidates for a counterexample to the Leroth problem, namely a unirational variety which was not rational. So it took almost 100 years, or more than 100 years, before we actually knew that this was stably irrational. This was proved by Hast and Schinkel. And it was known that also in higher dimensions that these complete intersections are unirational. Yeah, so we settled a fourfold case, which is somehow a little bit harder than the threefold case. And we also give a new proof for the dimension 3 case. And one way to think about this result is that this sort of settles the rationality problem for all complete intersections in dimension at least, or at most 4, except for the missing case of cubic fourfolds. So this was sort of the last piece in or second to last piece in the classification. Okay, so I'll tell you a little bit about this proof towards the end if I have time. Okay, and just sort of to give you another flavor of this paper, we get many other new results on complete intersections. For instance, I mentioned this sort of logarithmic bounds of Stefan Schreider for hypersurfaces, and we sort of yeah, we get analogous results in for complete intersections. But it's important to know that we use Schreider's results as input for irrationality. So yeah, his work is definitely a key ingredient. Yeah, so for instance, in dimension 5, all of these cases here are now known to be stably irrational. So I mean, here we have a complete intersection in let's see, P10 of 5 quadrics, and all of these cases in bold, they were new. So we get many new results using this technique. Okay, and also, I mean, there's no reason to restrict to hypersurfaces in PN. We get results basically in any toric variety, and in particular for these products of projective spaces. And one example is hypersurface in P1 cross Pn. So we fully classify all the bidegrees corresponding to rational hypersurfaces. So these are a little bit more interesting than, I mean, than the usual hypersurfaces, because they are now sort of fibrations over P1 into hypersurfaces. So there's a little bit more geometry in this case. And the theorem is now that such a hypersurface in P1 cross Pn is stably rational if and only if, well, A is 1. Well, in that case, the hypersurface is birational to Pn via the second projection. Or B is at most 2. In that case, X is a quadric bundle over P1. So again, it's rational by sort of known results on quadric bundles over P1, this sense there. So basically, you have this sort of 2 obvious cases that have to sort of be dealt with. Those are rational, and all of the other ones are irrational or stably irrational. Okay. So let me say a little bit about the proof. So there are sort of various ingredients appearing here. Maybe the most important one is the results of Nicaise and Schinder, and also Kontsevich and Schinkel, about specialization of birational types. It's certainly, I mean, our method is based on a degeneration argument, and basically this result here says that stable rationality, it specializes in families. So we can sort of deduce that something is irrational on the generic fiber by going to a special fiber. To construct sort of interesting degenerations, we use tropical geometry, and in particular, toric degenerations. This is a very useful tool, and it basically gives us a lot of flexibility in constructing degenerations that we then look at. And it's in particular useful because we can relate sort of rationality problems for, say, hypersurfaces to rationality problems for other varieties, and in particular lower dimensional varieties. And here, of course, we need some sort of irrationality input, and so yeah, we need stuff like the Art and Mumford example or the examples of Schreider as sort of an irrational input in our proof. So yeah, that's basically the 3 main ingredients. Yeah, all of these are sort of quite recent. Yeah, okay. Yeah, so first I'll explain the first part here about specialization of birational types. Maybe now is a good time for questions, if there are any.
John?
Yeah.
When you were showing us the table with stable rationality and stable irrationality, so
Mhm.
in this here, the line which divides stable irrationality and rationality is kind of growing, increasing. Is there a conjectural position of where we should have the separation between stable irrationality and rationality?
Yeah, I mean, there are many, basically, yeah, there are many sort of folklore conjectures lying around here. I think there's a conjecture of Collar's basically saying that anything in in degree 4 is irrational. So basically, we don't know anything about stuff with degree higher than 3. So yeah, but yeah, there's nothing precise. I mean, from now on, this, I mean, people, yeah, I mean, this result of Schreider was sort of very surprising because there was a logarithmic bound here, and people maybe expected there to be sort of some sort of magic slope of degree dimension ratio, but now maybe it could be that Collar's conjecture is true, that basically anything in higher dimensions of degree higher than 3 is irrational. So yeah, I'm not completely sure what one should expect, but certainly there is that conjecture of Collar.
Thank you very much.
Okay, should I go on maybe? Yeah. So just to explain what the specialization theorem is, let me define the set SFB. No, FBF. So F is a field, and SBF is the set of stable birational equivalence classes of varieties over F. Okay, so basically we have function fields over F. And for each x, we denote bracket x with a subscript SB, denote the equivalence class of x. So it's an element of this set. And we will consider the sort of just a group, the free abelian group generated by the set of equivalence classes. Yeah, so an element here is just a formal sum of birational equivalence classes. Okay, so if you have any scheme over F of finite type, well, maybe it has many components, and in that case, we define the class of X to just be sort of the sum of the components. And in particular, if X is non-reduced or generically non-reduced, you still just take the reduction. So yeah, so this operation really doesn't see the non-reduced structure here. Okay, this is a priori a group, but there's a ring structure here by the fiber product over F. And yeah, of course, there's a much more natural way to view this. This is due to the Larsen and Lund theorem from the early 2000s, basically saying that if you take the Grothendieck group of varieties, so basically the same thing, the formal group on isomorphism classes of varieties, and then mod out by the scissor relations. Then if you divide out by the class of A1, then you get exactly this ring. And the isomorphism is induced by sending a class X in this ring here, the Grothendieck ring of varieties, and sending it to the class of stable birational types. it's important to note that this map here only works for X smooth and proper. Yeah, so yeah. Okay, so just to introduce some notation for the specialization result. So we work over the field of Puiseux series. So it's all of these power series rings here. And you have a corresponding valuation ring, which we'll denote by R. And basically we'll consider schemes defined over this, this ring R. Maybe you've already seen this, but we say that a scheme R is strictly semi-stable if, well, Zariski locally, you can view it, or you can have an Natal neighborhood which is isomorphic to just sort of a union of hyperplanes. So the picture really looks like this. So you have here we have a scheme over R. We have a generic point. Typically, this will be maybe a smooth K variety, but there will be a special fiber, and here the singularities are locally of the form like hyperplanes intersecting. Okay, so yeah, this is the this is the setup. Right. So now we can explain this result of Nicaise and Cinder. So we take some proper and semi-stable model over this DVR with maybe a reducible special fiber. And well, basically Nicaise and Cinder proved that there's a unique ring homomorphism from the ring of stable birational types over the generic fiber to that on the special fiber. And there's an explicit formula in the case where you have a proper and semi-stable model. So in that case, what you do is you take your variety over the special over the generic point, and you take some, you extend it to a proper model over this ring R, and then you send your class to the alternating sum of all of the strata that appear in this the special fiber. So there are a bunch of smaller subsets here. They're indexed by the components in the special fiber, and we take all of the intersections, and you take the alternating sum. So this is something that's defined over the special fiber, and yeah, it turns out that this is independent on the sort of chosen model over R. Yeah, so this is a remarkable result because it sort of relates a rationality problem over the generic fiber to that on the special fiber. So this will be sort of maybe the crucial ingredient in the proof. Okay, so let me just say a few words why this is sort of a remarkable theorem. Well, okay, so what I just described to you is called the motivic volume. This function, or this map, it sends the class of a point to the class of a point. And basically, you know, in our whole story, we'd like to check whether a given variety is, you know, has the class of a point in this ring here. So if we can take X and say that the class is different from the class of a point, that's by definition saying that X is not stably irrational. And this simple observation that the volume sends a point to a point gives us a sort of way to obstruct the stable rationality of the generic fiber. Because if we if we write down a family and take this alternating sum and see that it does not cancel to the class of a point, yeah, we're done by this observation. Yeah, this is the thing I just said. So we write down the degeneration, has many components maybe. If this alternating sum here is different from the class of a point in this ring, we're done. Then the generic fiber is not stably rational. And even in the case where you don't have many components, this is a remarkable theorem, because yeah, if you have a smooth family over R, then this alternating sum here basically just reduces to the special fiber itself. And then basically the conclusion is that stable rationality specializes in smooth and proper families in characteristic 0. So if you have a family of rational varieties and everything is smooth, then the limit will also be rational. A priori, this is not obvious at all, and yeah, it was in fact a very long-standing conjecture. But for us, our main interest will be sort of this observation here, that we will construct degenerations and then try to argue that these alternating sums here do not cancel out to be a point. In fact, sort of the more components that we have, the main idea is that having many components actually help in this story. So and then we're looking at more strata, and we have more potential to relate these strata to sort of lower dimensional examples. Okay, so our takeaway here is this formula here. If this alternating sum here is different from a point, we're happy. Okay, so yeah, maybe I'll go through this quickly, but there's a sort of very quick application here. It's due to Claire-Bassin. So if you look at a very general quartic double solid, this is stably rational. So these are threefolds that are obtained by double covers of P3 branched along a quartic surface. And we can prove this very easily using the previous observation. We just degenerate to the Artin-Mumford example. Yeah, the Artin-Mumford example is also a double quartic threefold, but now it's of course singular. And the main point is that this Artin-Mumford example is has a non-trivial Brouwer group, so it's non-stably rational. And yeah, from there we're basically done. I mean, one has to be a little bit careful because one needs to write down semi-stable degeneration here, and this is a little bit subtle because of the singularities of this example, but the singularities are mild enough so that they don't really contribute anything to this this previous formula. Okay, so here we have a situation that degenerates from irreducible to irreducible, and we still have this well, application. But yeah, for our applications, we get better results using degenerations with many components. And just to once again reiterate here, well, irrational strata of low dimension may be shown out to not cancel out in the alternating sum here. And if that happens, this generic fiber is not stably rational. Okay, so that's the main idea, and to just carry this out, we now need to write down degenerations. Yeah, and for this we use you know, tropical degenerations.
Is it okay if I ask a quick question? Sorry.
Yeah, yeah.
I'm just trying to, you mentioned this thing about singularity. So, you know, if I were to, you know, people like this example of taking a quartic surface and degenerating it to 4 planes, and you get singularities in the total space there. Are those singularities mild enough that they don't matter from your point of view?
Yep. Yeah, that's true. Yeah, basically all toroidal degenerations are allowed like that. So the story that I'm phrasing here is a little bit too simplified. Typically, what you would do is you write on the family and then you resolve. And luckily, the singularities are sort of nice enough so that the strata that you add by blowing up, they don't sort of contribute to this, you know, irrational piece that happens in this sum here. But certainly the degeneration that you just mentioned, degenerating into degenerating a hypersurface into a union of divisors that intersect transversely, that's certainly also fine. Yeah.
Yeah, I guess I was wondering because, I mean, in those situations, the total space is singular, right? So I was sort of wondering where that comes in. But anyway, yeah.
That's right. Yeah. So there's a sort of subtlety about that I'm not discussing, but in fact, we don't need to worry about that. Like any toroidal degeneration is also fine in this story. Yeah.
Thanks.
Okay. So I mean, I realize that you all know about the tropical degenerations, but let me just do it quickly. So just to set up the notation that I'll need for later. So,
John, in the example that you were saying before of the quartic, you can blow up the singularity. You obtain some divisor that maybe don't have multiplicity 1. Is it a problem?
In that, no, it's not a problem. So first of all, this in this this ring here, we don't care about the multiplicity at all. So 2 times d is the same thing as d in this stable birational types. And I mean, as you know, these singularities are just nodes.
Yes.
So if you blow them up, they're rational, and yeah, so there's no problem here. Yeah. Yeah, sorry, I was a little bit quick in this example, but I want to focus on the sort of more sophisticated degenerations. This is sort of a very baby case of the theorem. Yeah. All right, so I'll start with a lattice polytope corresponding to a projective toric variety Y. So here you see the polytope of P3 polarized by O of 4. So if you take a regular subdivision of this polytope, well, what does that mean? Well, basically we take a function on, well, an integer valued function on this on the lattice points of delta, and we take the sort of lower convex hull of this function. This induces subdivision by taking the graph and then projecting all the faces down to delta. So it's a special type of subdivisions of a polytope that we'll be interested in, because they will give us degenerations of the toric variety Y. But this is the picture. So yeah, and the main point is that this subdivision induces a degeneration of Y into a union of toric varieties, 1 for each face in the subdivision, and they sort of intersect in a way that sort of reflects the combinatorics of the subdivision. So if you have 2 intersecting faces in P, then the corresponding toric varieties intersecting in another toric variety that that's specified by that face. Okay, so it's a quite useful thing to work with these subdivisions. So let me maybe do one example. So if we take the polytope of P1 cross P1 with the polarization 1, 1, so that would correspond to the unit square. And if you subdivide like here, you add the diagonal here. Basically, you see two polytopes, and each polytope corresponds to the standard polytope of P2 with the polarization given by O of 1. So of course, what happens here is that you degenerate the quadric to a union of planes that intersect along P1, and the P1 you see here. Yeah, and maybe a more sophisticated example, we take P3 and with the quartic again, and we maybe degenerate using this subdivision here. So here I just insert this small square here. So now we have sort of two maximal components, or two maximal faces that intersect along P1 cross P1. And this corresponds to the degeneration of P3 into a union of two toric threefolds, yeah, which intersect along this surface here. Okay, so basically, our main application will in fact use that this very degeneration. Like we're not interested in P3, but basically doing this in P6 will give us the main example. Okay, so if we take Larsen polynomial with the Newton polytope delta, we can for every phase in the subdivision we get a new polynomial just by sort of picking out the coefficients appearing in the phase. And there's a sort of non-degeneracy condition that we need in order to do this. We require that all of these smaller hypersurfaces are smooth for every phase. But if we have that condition, then basically our earlier motivic obstruction here, it takes the form that while we take our polytope, we sum over all of the faces in the boundary, sorry, not contained in the boundary. And if the alternating sum here is not equal to the class of a point, maybe up to some sign here, then a general hypersurface with this hyperplane, no, sorry, this polytope will not be stably rational. So it's basically, yeah, it's a translation of the earlier observation, but now into sort of a more combinatorial statement. But yeah, the advantage here is that this is a very easy thing to check. I mean, this is a sort of a genericity. I mean, this is true sort of generically, and yeah, we can use this to actually generate the irrational example. Okay, so now we've set up the sort of enough theory to actually prove the main result, and I'll do this in sort of one slide. So here's the proof why the quartic fivefold is stably rational. So we take the sort of standard simplex. Well, it's scaled, I guess. So this is the Newton polytope of a general quartic fivefold. And if we take this subdivision here, well, it sort of looks like the one we just wrote down for P3. So if we just add some more faces also here, we get a degeneration of P6 into 4 toric varieties, and yeah, and they should intersect like in this picture. Okay, so the red polytope in this case, that corresponds to a 2-2 divisor inside the P2 cross P3. And that's red because this is the most important polytope. This is something that's stably irrational. It's known to be stably irrational by sort of known results by Hassett, Piruk, and Schinkel. And this is sort of the irrational input that we need in order to conclude. And all of the other polytopes in the picture here, they have lattice width 1. So what does that mean? Well, basically all the polytopes that you see in the picture, they can be squeezed inside you know, 2 hyperplanes with just distance 1 apart. And if you think of the Newton polytope, that means that the hypersurfaces that we look at with the corresponding Newton polytope, those are linear with respect to a certain variable. And if you have a hypersurface which is linear with respect to one variable, it means that it has to be irrational because you can solve for that variable. So we have a degeneration of the whole polytope. So there's sort of one complicated polytope which does not have lattice width 1, but all of the other ones have lattice width 1, so they are rational. And so if you look in this alternating sum, basically you'll have like one irrational piece, and then the rest just irrational piece. You have one irrational piece, and then the rest rational pieces. And while there's no way that you can cancel out something irrational by something rational in this this ring on stable birational types. So the whole thing does not cancel out to the class of points, and therefore we're done. Okay, so maybe I would pause here for some questions.
John, can you please repeat what was the role played by the hypothesis of Newton on degeneracy?
Oh, it just means that if you restrict to each each of the faces here, that your polynomial should be sort of smooth in here.
Yes, I understand what it means. Can you explain why is it there?
It's just for convenience. I mean, we need to deal with singularities in this to apply Nicaise and Schindler, and yeah, basically, it's to, because if you have such a degeneration of these toric varieties, then you get a corresponding degeneration of the hypersurfaces, and we need these components to have mild singularities. And yeah.
Thanks.
Yeah. Okay, so so this is a strategy that sort of, okay, there was one thing I wanted to say. So here we have a result about quartic fivefolds, so dimension 5. But the sort of irrational input here is from this smaller polytope. And this corresponds to some fourfold inside P2 cross P3. So I think it's quite interesting that you deduce irrationality of a fivefold from sort of a fourfold. And I think this is the main strength of this method, that when you degenerate to many components, some of these strata will have very small dimension, and then yeah, hopefully you can degenerate to some case where this is even irrational, and then if you can make sure that sort of the other components are rational, as in this example here, then yeah, then we have a quite good strategy. So So this is what we basically utilize in the paper. We write down explicit degenerations with many components and then use this strategy. Okay, so let me explain one more example. So here, in the previous example, we basically had, we degenerated P6 into 4 toric varieties, but basically we can do. This is a very computational technique, so one could try to do something more involved. So I'll try to show this in one example. So if you consider a very general 2-3 divisor inside P1 cross P4, well, those are stably irrational. And in fact, if we know that this is stably irrational, then sort of all of the other bi-degrees follow from sort of degenerating into this. Yeah. Okay, so this is not so important. I just say that the hardest case in P1 cross P4 is exactly this 2-3 divisor. Okay, so let me explain the proof of this theorem here. So I mentioned this Hasse-Purka-Chinkel quartic earlier. This was the sort of main irrationality input for the quartic fivefold, and it's also the irrationality input in this example. And it's given by this equation here. So it's a fourfold inside P2 cross P3, given by this equation. And Hasse-Purka and Chinkel proved, and also Schreider, that anything that specializes to this fourfold here is not, or does not admit the decomposition of the diagonal, and hence it's stably irrational. And it's a very remarkable thing, because this is a fourfold which is very, very singular. I mean, I think it has maybe 7 components inside the singular locus, but still the singularities are sort of mild enough to imply that the generic 2-2 divisor inside P2 cross P3 is also stably irrational. But the good thing for us is that there are very few monomials in this example. So if we look at the Newton polytope of this quartic, it's given by the convex hull of the columns of this matrix here. So here you would have 0, 0, 0 corresponding to 1, or a constant, and then you would have yeah, these other monomials. Okay, so the starting observation is that we can take this small but still irrational polytope and embed it into the Newton polytope of a general 2-3 divisor. So the Newton polytope of a 2-3 divisor is given by, well, basically the product of these two polytopes. And one can see that that embeds, because while the polytope is given by setting or u has to be less or equal to 2, and the sum of the other variables is less than 3, and this is clearly the case in this matrix here. So the top row is always less or equal to 2, and then the sum of the remaining entries, it's at most 3. And indeed, we can just write down an explicit 2-3 polynomial that dehomogenizes to the Hasse-Purka-Chinkel quartic. So in more geometric terms, it means that well, if we take the Hasse-Purka-Chinkel quartic, restrict to the torus, we can recompactify it inside P1 cross P4, and then we have this. Okay, but of course, this is good, because now we have something that's stably irrational somewhere. And now we can basically do the whole thing from before. We can write down a degeneration. And to write down a degeneration, we specify a regular subdivision. And basically, we want the polytope that we just mentioned to be one of the, I mean, that should be one of the polytopes in the subdivision. So if we use the distance function to this polytope, then that's a fine function, and which defines regular subdivision. And yeah, and basically this is 0 if and only if you're in that polytope. And so you get a subdivision of this product polytope. But now it's, I mean, this is if we do this, we get a subdivision which has many cells. It has 26 cells, and yeah, quite a lot of, or sorry, 26 maximal cells, but of course the numbers here are quite big. And it corresponds to degenerating P1 cross P4 into a union of 26 toric varieties. And of course, again, you have this sort of one irrational polytope that, well, this Hasid-Pirukachinko polytope that appears somewhere inside this subdivision. And yeah, so basically what we have to do is to go through all of the other phases, and we have to check that they correspond to rational hypersurfaces. And yeah, this is a finite computation, so and we just do that. And most of the time we'll be lucky, and the phase will have lattice width 1, so it would again be rational. And sometimes we have to sort of use some known results on, maybe you would get a sort of quadric bundle over P1, so it's known to be rational, or a conic bundle over P3 with a section, that's also rational. But in any case, it's sort of easy to go through those extra phases and see that everything else is rational. So if we again compute this irrational, or this motivic volume, we see that we get one piece corresponding to this irrational guy, and then these other classes, which are sort of all rational. Okay, but yeah, there's no way you could cancel out this thing to be the class of a point, and so this 2-3 divisor is stably irrational. All right, so just some end remarks. This is sort of the general strategy. So you have your irrationality problem for maybe complete intersections or hypersurfaces, something like that, and you construct degenerations by subdividing polytopes, and the idea is that all of the lower dimensional, all except for one lower dimensional strata is stably rational, or make sure that these intersections do not cancel out. But I think it's a quite flexible strategy, and yeah, I'm pretty sure that there are more examples to be found. All right, so let me maybe end here. So yeah, thanks for listening.